Okay, it's recording now. Welcome everyone to come to CNTC seminar today. It's my pleasure to introduce Professor David Huse from Princeton. David is very well known in statistical physics and condensed matter physics. He did his PhD in Cornell, and he was then in Bell Lab until moving to Princeton. Today, he's going to tell us about many-body localization transition. Please, David.
Okay. Hello. So we're going to use the Blackboard today, which some of you might be missing. Okay, so here's the title of what I want to talk about today. So I'm going to focus in particular on this novel phase transition that we've been studying, I guess now for 15 years, between many-body localization and thermalization. As I'll say, it's not a thermodynamic phase transition, it's only in the dynamics. So it's an unusual type of phase transition. It's as far as we know, it only occurs in quantum systems. So in that sense, it's a quantum phase transition, but it's not in the ground state. It's in highly excited states. And in fact, we typically just study it at infinite temperature in the kinds of models we study. So it's an unusual type of quantum phase transition. We just recently posted, actually it was just published in PRP yesterday, I think, a paper with my student Alan Morningstar and John Embry. That's sort of the latest installation in this story, which has been going on for quite a while. There's a lot of earlier work that I will mention as we go along. Okay, so what are we talking about? Actually, in some sense, it's down here at the bottom. We're asking of a quantum many-body system, is it a bath for itself? Can it bring itself to thermal equilibrium, or is it unable to do that? So we're asking, is this system a bath, or can it be a bath for something else, or is it unable to do that? And that's what this phase transition is. Systems which are localized, many-body localized. So many-body localized is abbreviated MBL. They're stuck in a state near the initial state, and they're unable to explore the states, and they're unable to be a bath for themselves. Whereas other systems which are not localized, generic systems that are not integrable, not localized, in the limit of a large system and large time, they will go to thermal equilibrium, as we always assume in statistical mechanics, right? But many-body localized systems actually don't do that, in spite of being interacting in a certain sense,
David,
integrable, although in another sense integrable in the
hey,
statistical.
David,
Okay.
David, this is Shankar. May I ask you a question, just semantics? So this is all for quantum system, what you're saying, but this ergodic and integrable, that applies equally to classical systems also. The same question arises in classical systems also, whether it is a statistical mechanics question, whether a system self-thermalized.
Absolutely, absolutely.
Yeah.
And certainly the conventional integrable systems, beta-ansatz type integrable systems, there are direct analogs in classical.
Okay, good. Okay.
But as far as we know at this point, many-body localization does not occur in classical models as a strict case.
But can we absolutely rule out that there may not be some deep ability we don't know about?
That's not an absolute statement, but certainly it appears right now that for quantum systems, many-body localization is a phase which is generic. It's stable to generic short-range perturbations. So in that sense, it's not a fine-tuned phase. Whereas if it exists classically, I think it's highly likely to be a fine-tuned thing like other forms of integrability. But that's an open question, and let's just leave it aside.
Okay, good. Thank you. You have answered the question. Thank you.
I'm just talking about quantum systems. Okay. So And in particular today, I'm going to focus on a particular case of the MBL transition, which is the one which is most studied that we've been working on, which is one dimension, short range interactions, and random. Okay, so let me just give a bit of an introduction to it, right? And so we're talking about isolated quantum many-body systems, thus no environment. So the system, if there's going to be a bath which is going to bring the system to thermal equilibrium, it has to be itself, right? The system serves as a bath for itself, or more precisely, this full system serves as a bath for the subsystems. In particular, I will consider right now one dimension. So we have a chain of either spins with random fields or lattice particles, particles hopping on lattice with random potentials, right? And of course, this is the context of the usual discussion of Anderson localization, particles in static random potentials. But in one dimension, you can always just convert them to spins, right? And so, in some sense, spins are nicer to think about. And we're just, for starters, going to only have short range interactions. At the end, if there's time, I'll try to relax some of these things, 1D, random, short range, and ask what happens with longer range interactions, what happens with non-random cases, what happens in higher dimensions. But we may not have time for that. Okay, our system, it's closed. It has some dynamics given by its Hamiltonian, which might be time independent. And if you're most comfortable thinking about just time independent Hamiltonians, that's fine. I'm actually not going to be that specific about it. But it also could be a Floquet system where the Hamiltonian is a periodic function of time. And Floquet systems are actually nicer because you can make a Floquet system with no conservation laws, no energy conservation, but still it's an isolated quantum system. And it still has this phase transition, and it's purely this phase transition. You don't have something else going on. So I think the Floquet systems are the nicest in place to look at MBL because you don't get distracted with transport of conserved quantities and all sorts of other conservation laws which might be making things confusing. But that's not too crucial for anything I'm going to say today. Okay, and then we're going to be under conditions where if the system did go to thermal equilibrium, its entropy is extensive. So we're not talking about ground states or very low temperatures or highly polarized states. We're talking about just random states drawn from the middle of the spectrum. And so often when we study our spin chains, we just take an arbitrary eigenstate or an arbitrary initial condition, which if it thermalized would correspond to infinite temperature. And that's a fine place to work for the basics of studying MBL. Okay, so it's a phase transition in the dynamics, not in the thermodynamics. And so let me just draw one parameter phase diagram like this. So this is the parameter I'm going to adjust, which we could think of as turning up the randomness going this way. So making the random potentials or random field stronger is going this way, or turning up the interactions going this way. So it's the randomness that enhances localization. It's the interactions that enhance thermalization. And we're going to have a phase transition between the Mbl phase here and the thermal phase. So here there is no self-bath. It's not a bath for itself. And over here, ETH, the eigenstate thermalization hypothesis, is true, and the system does go to thermal under its own dynamics in the limit of an infinite system in infinite time, right? Like all phase transitions, it's only well-defined in the limit of an infinite system. And in this case, because we're talking about dynamics, we also need infinite time. So here, between these two phases, we're going to have a sharp transition in the limits of length going to infinity and time going to infinity. You have to take both those limits to have the sharp transition. And And that's going to be my focus today, is this phase transition. Okay. And now there are other cases, as I said, you could be in more than one dimension. You could have no randomness, instead be quasi-periodic, producing the localization. You could have long-range interactions. Of course, you could have finite size effects, finite time effects. And so there's a lot of other things to think about in MBL than what I'm going to talk about today, but this is a theory seminar, and I'm going to focus in particular on how we approach this phase transition using the renormalization group and what's been learned there.
Excuse me,
Okay.
Can I ask a question?
Yes, please.
Right. So is there I understand that lots of results show that interaction enhance delocalization, but is there a way to think of why that's the case when the interaction is, say, very large? Say we know from ground state property, there's like mod insulator when.
Yeah, right. So saying interactions, so when the interactions are weak, yes, interactions enhance thermalization. If you take the interactions extremely strong, it can be the other way, that high it can be reentrant, right? So if you go very strong interactions, you could go back into an MBL phase. So I'm not saying interactions monotonically enhance thermalization.
I see.
So let's just say that the regime where the phase transition tends to be at rather weak interactions, where it is this way. Turning up the interactions makes it thermalize. But yeah, you're absolutely right. If you go very far to very strong interactions, strong compared to the randomness, you can actually get into regimes where the interactions are what's causing the localization to some extent.
I see. So just to make sure, so when the interaction is very strong, it seems like that re-entrance of localization is not just a ground state property. It's also like mid-spectrum state. That's also the case?
Oh, absolutely. Yes.
Oh, okay.
Right. No, those effects can happen. It's basically just a very strong interaction is like a constraint, right? You have some dynamics. The dynamics, let's say it was Hamiltonian, it conserves energy. And if you have very strong interactions, there will be a whole bunch of processes which will effectively be forbidden because they're so far off shell.
I see.
Right? And that can help produce localization.
I see. Thanks.
But for today, think we're in the regime, we're studying the MBL phase, we're adding interactions to it, strong enough to produce thermalization, but never very strong interactions. That's like a different regime of the phase diagram.
I see.
Yeah, no, that's a good point. Okay, so we're going to look at this phase transition using the strong randomness, which is a real space method, renormalization group. And this method goes back to Dasgupta and Ma long ago. And of course, Daniel Fisher really turned it into a systematic enterprise in the 90s. But that was all for studying in the quantum domain, for studying ground states. But then when people started looking at MBL, which is highly excited states, it certainly looked like the scaling was, the systems were, if you thought about them in an RG terms, flowing off to infinite randomness. So sort of what you might call drifts to strong randomness, or let's say stronger randomness. If you do finite size studies and you look at probability distributions of things, and then you ask, as we do bigger and bigger samples, do these probability distributions get broader and broader? And that's the behavior of a flow to a strong randomness fixed point. And these drips to strong randomness were seen in a lot of the numerics. You know, we first saw them in a paper with R.G. Paul's thesis. It was, you know, we were seeing that already. We proposed a strong randomness scaling, but we couldn't really get very far with it at all at that time. There was a paper from Lewitz and Clark, Brian Clark, David Lewitz in 2016, and then with Vedika Kamani and Donna Sheng, we also found such evidence. So this is you know, a lot of the studies of this phase transition and of MBL are numerics on, unfortunately, extremely small size systems. And it's hard to, you know, decide what to conclude from those studies with much confidence, but these numerical, so here I'm just talking about numerics, these numerical studies were able to see evidence that the behavior of the system was becoming effectively more and more random, more and more sample to sample differences as you go to bigger samples. And you can think of that as an indication that if you could do an RG for it, it would flow, it'd be flowing off towards stronger randomness. Okay, and so what you do in these strong randomness renormalization group studies, which Fisher made systematic, is you assume your system is highly random. And that means the probability distributions of the local couplings in the Hamiltonian are very broadly distributed on log scales, right? So that, you know, terms, some terms are orders of magnitude bigger than other terms. Right? And then you ask, in that limit, you can treat the weak terms in perturbation theory relative to the strong terms, and you can develop a systematic approach.
So David, I have a question. I have a question on this point, which is almost like a mathematical question. So are we talking about infinite randomness, or are we talking about arbitrarily large randomness?
Well, the basic question is, okay, so the control of those calculations, which, you know, some of the calculations for quantum ground states are really fully controlled. Yes. And the control of that calculation is in the limit of infinite randomness. Mm-hmm. So you work near that limit, you do the renormalization, and you find the renormalization group flows brings you even closer to the limit, right? Okay, so it's in the same spirit here. It's in the same spirit here, like Dasgupta Ma. The spirit is the same. Right, and that's what we're going to do here as well. We're going to assume we're, you know, our course, so we're assuming, let me, okay, so this will be the program. Assume, first of all, we're going to coarse grain the system and look at it. And let's just not bring up numerics, because I'm going to assume we're coarse graining the system to a scale beyond what we can access numerically. And let's assume that when we do that, the coarse grained system, you know, is at strong randomness in this sense. But it's, you know, the way we're going to do this is rather different than what Fisher does. It involves more assumptions. It's less controlled. But we want to develop the strong randomness renormalization group so that it can deal with this phase transition, right? And that's been a project that's been going on for quite a while. So the first papers, right, and basically, let's just say do this RG. By do, I mean, it wasn't a matter of just systematically doing it. It was a matter of figuring out how the hell do I do this, and then making a number of attempts. There have been quite a few papers, and gradually getting something which is more and more satisfactory, and seems less ad hoc, although it's still got lots of assumptions in it. Okay, so this started with, let me just give credit to the early work. So Potter, Vasseur, and Parameswaran, however it's spelled. These guys at Berkeley, and then we were working in parallel. Ronan Vosk, who was a Ehud Altman student, myself, and Ehud Altman. The first papers really trying to do this at some level were in 15, these two papers. And then, yes, so anybody, please interrupt with questions. Of course, I know Sankar doesn't need encouraging for that, but everybody else, just yell out. Okay, so this is an enterprise specifically about the strong randomness normalization group for this problem, which has been going on for a little over 5 years. Right, but then there was an important paper that sort of got us to what the story I'm going to tell you today from Makina, however it's spelled. Again, Vasseur, Roman Vasseur, and Max Serbin. And this was 19. And they showed a Kosterless Thales like RG flow. And that's what I want to tell you about today. And then they still, they arrived at that through some routes with, various assumptions and leaving out a bunch of the physics. But as soon as I saw this paper, my student Alan Morningstar and I started working on this, trying to put in more of the physics and do it in a way that seemed better to me, and that's what we've been doing, and leads to the work I'm telling you about today. So there was a first publication with just Morningstar and myself, and then the most recent one with John Embry. John Embry came by Princeton the week before the pandemic, and he had some ideas about how to do the thing better, and then we've been implementing that, and that's what happened this year. Okay, so we've coarse-grained the system. We're near the transition. We've coarse-grained the system. We're assuming it's at strong randomness. And so what we're going to do is we're going to look at our sample. So here's our sample, and it's 1D. So this line is my sample, and it's infinite. So it just goes all the way across. And when we coarse-grain it, it has local properties which are locally like the Mbl phase or locally like the thermal phase, right? It's near the critical point, but it has strong randomness. So some parts of it are way over here and some parts of it are way over here, right? And that's the picture we're going to take. Assume that that's true, right? And so that means some parts of it are very localized and some parts of it are quite thermalizing. And it turns out when we work all this out, and this has actually been known right from the beginning, that when you coarse grain near the transition, the system is mostly localized with small islands of thermalization, there is a real imbalance of power between thermalization and localization, which is well known to quantum experimentalists. Thermalization is decoherence. Many-body localization is coherence. And you know, if you have a little bit of decoherence, it can destroy a lot of coherence, right? This is well known, and this is the basic problem of, for example, building a quantum computer, okay? So this is now my sample. I've coarse-grained it, and what it looks like on the scale we're looking at is some widely spaced small islands, which are, so T means thermal. And this little region, if I cut it out and looked at its spectrum and its eigenstates, they would all be volume law entangled, where the volume is the length of this little region. It's highly entangled in here, and the dynamics do thermalize, at least on the scale of that size, right? And then in between are these, we call them I for insulating, which is, they're really Mbl regions. And so that's what the sample's going to look like as we've coarse-grained. So it's a real space picture. Strong randomness. The strong randomness assumption is we have these contrasts, right? The distribution of local properties is spread way out on this axis, so I can say these regions are thermal, these regions are Mbl, and that is a separation which exists. Okay. So, right, so this is what it looks like. So we call these blocks. So this is a T block. I'm going to say the word T block, and this is an I block. Just means a patch of the sample that's locally insulating, a patch that's locally thermalizing. And by insulating, I mean many-body localizing. Okay. Now, we're going to have a real space cutoff, which is a length. So because it's, I'll call that lambda, so that's a length. And then the T blocks are going to have length. So L is the length of the T block, and it's going to be greater than or equal to the real space cutoff. So everything, well, I'll tell you how it goes. So we've coarse-grained to this length scale. And so our shortest T blocks are at that length scale. And there's longer ones. And if we're near the transition, these T blocks are length scales near the cutoff. They have a distribution, and they're widely spaced. So which means the I blocks are much longer than the T blocks. And at this point, the randomness is in the lengths of the T blocks, let me put T on there, and their locations. The randomness is, I've got randomly placed little T blocks, and they're of random length. And so what we have is a function, rho L sub T. This is the density of T blocks of length L sub T. It's a function, so we're going to have, and this is typical of these strong randomness RGs, it's a functional RG. This is what we're going to renormalize, is this function plus one other parameter, which is the one parameter characterizing the interactions across the I block. So this is an insulating region here. Any couplings across the insulating region decay exponentially, and there's a decay length for that, and that will be one other parameter. So our RG is going to have a parameter, which I'll call zeta, which is a decay length for interactions across the I blocks, one parameter plus a function. So therefore, it's a functional RG.
David, do you need to assume the disorder distribution here?
Well, the disorder distribution is here, and it'll show up as the distribution of the lengths of these blocks. And then
You need to
the
assume
placement of these blocks is random, except for a constraint that there's a minimum length on the I blocks. So
Okay.
that's what I mean. The randomness is in, and this is self-consistent, right? If we, the RG only produces this type of randomness. The length of the T block is a random number drawn from a distribution, and then they're randomly placed with really no correlations other than a short-range constraint that they're not near each other, right? The I blocks have a minimum length. Beyond that, they're just randomly placed.
When you say the correlation decay in the I block, do you need to assume it's exponential decay, or you don't need to assume the form of
This has to be an exponential decay. I'm going to talk about that. And then another point is, you might think the different I blocks were different. Some were more localized than others. And it certainly appears that that randomness is irrelevant. So we can treat the I blocks as essentially non-random, all having the same decay length. Okay, so what's the basic physics here? So the basic physics here is the T blocks are trying to thermalize the I blocks. It's a competition. This is a little mini bath, and it's trying to thermalize its environment. And the basic process looks like this. Okay, so we build the RG is built on a story about this situation here, where you have a little bath here, which we treat as if it was a random matrix, and it's coupled to this localized region. And the question is, okay, so sorry, let me say, so the I blocks are localized, right? And so the way to think about this is, I've got this coarse graining. Let's now cut the couplings at all these boundaries and look at the properties of this region and this region. In this region, like I said, the eigenstates will be fully entangled across the T block. In the I block, if I cut it out, it's really localized. It has localized conserved operators, localized integrals of motion, or L bits or whatever. So the I blocks have L bits, which are localized conserved operators, if we detach them from the T block. So if I cut it out and look at the dynamics of this region, it's fully localized, and it has these conserved operators, which are localized on a length scale much shorter than the length of the I block itself. So then, now we're going to turn the coupling back on, and there is this analysis of, does it succeed in thermalizing does the T block succeed in thermalizing these localized operators or not, right? And this is something that Deruk engineers looked at, and we're following on what they found. And this is what's called misleadingly the avalanche. Okay, it's misleading to call it an avalanche because it's very slow. Avalanches aren't slow. But it's like an avalanche in that the question is, once it gets going, does it stop or does it just keep going? Right, and we're asking that question. Okay. So how does that go in this context here? Okay, so we have a T block here, and then we have I blocks next to it. This is of length L. I'm always measuring my lengths in qubits. So something of length L contains 2 to the L quantum states. The entropy is L log 2 if it thermalizes. Right? Okay, now we've cut the interactions here first, and then we have L bits over here and L bits over here in the 2 adjacent I blocks. And now when we turn on the couplings, the end of the I block is going to couple to the end of the T block. So there's these local operators at the edges of the T block, which are the things which are going to couple to the I block, right? So we have, the T block has end operators here, which will couple to the L bits over there. Okay, and now, and we're going to assume the interactions that we turn on are of order 1. They're not weak, right? We turn them off, you know, to initially think about it. We didn't turn them off because they were weak. We just turned them off because it was the boundary between the thermal region and the insulating region, but the couplings is of order 1, okay? And now go out here at distance x, and here's an L bit. Right? This is a localized operator over here in the insulating phase. It has an exponential tail over to here. So when I turn on these couplings, there will be a coupling between this L bit and the T block, which can flip the L bit, right? Before I turn on the coupling to the T block, this L bit has a, you know, think of it, it's a spin a half. So it has 2 states, z equals plus or minus 1, up or down. And before I turn on those couplings, the eigenstates of this I block were eigenstates of all the local operators. They never flip. There was no flip terms in the Hamiltonian left once you went to the basis of these operators. Okay, that's what we mean by they're conserved. Right? If it's up, it stays up. There's no flip term in the Hamiltonian. But as soon as we turn on these couplings to the T block, there will be flip terms. So this will generate terms that will flip this L bit. And let me follow. Right, okay. So T block to L bit coupling gives a flip rate for the L bit, which falls off as, actually I was going to do this a certain way. Yes, 2 to the, I want to put some 2's in. So when you do these calculations, it's good to, because instead of using E, we use 2, because it's, you know, because it's all bits. So this is an exponential decay, and I just put a 2 here and a 2 here for convenience, right? So this L bit is coupled to this bath such that if this bath were a good bath, its lifetime for flipping would fall off exponentially in this way with a decay length. Right? So the important thing is there's this decay length over here, and there's the distance. Right? It's an insulator. Couplings are falling off exponentially with the distance with a characteristic length. And what's important is the flip coupling. Okay. So that's the assumption. We turned on that coupling. It generated such flip terms. Okay. You mostly with me? Okay, so the L bit's very close to the T block. This coupling will be of order 1. And the level spacing of this bath is exponentially small in the size of the bath. And these lengths are big compared to 1, right? So any L bit near to the T block will get entangled with the T block, right? Because this T block, it's a finite size system. It has a discrete spectrum. If you can probe it on an energy scale smaller than the spacing of those levels, you can see it's a discrete spectrum. But if you're probing it on an energy scale which is large compared to the spacing between the levels, it just looks like a continuum, and it's a fine bath, and you will get entangled with it, right? So the nearby L bits will get entangled with the T block because these couplings are of order 1 when you're close. And that's the avalanche. So then the assumption is the L bits close by, out to distance x, do get entangled with the T block. And then you ask, what about the next one? Does the next one also get entangled, right? So let's say entanglement goes to distance x, right? So now all these T blocks, all these L bits, sorry, out to distance x over here and over here have got entangled with the T block. And so I now have, when they get entangled with it, they actually join it and become part of the bath, right? So if the entanglement has gone to distance x, the level spacing of this putative bath is going as 2 to the minus L plus 2x, right? Because the total distance of this region which has thermalized is now L plus 2x, and it contains L plus 2x qubits. And so the level spacing is this, 2 to the L plus 2x, okay? And now this guy, now we look at the terms that flip this guy, and those are, right, this guy, these other L bits do not flip this. The first thing which will flip this guy is back here, right? Because that's the first operator which actually can couple to a flip operator over here, because in here it's all L bits and they don't flip it, right? Because this region was insulating before we coupled to this. So you have to go through the T block to flip it, right? And so this coupling falls off this way. So this is the flip rate, and this is the level spacing of the putative bath, right? But this will only be a bath which can flip it if this flip rate is larger than the level spacing, right? So if the flip rate is larger than the level spacing, then the bath looks like a continuum, and it can be a bath and you will get entangled with it. But when the flip rate drops well below this level spacing, it doesn't look like a bath, it's just a discrete spectrum. And this flip rate, it won't be able to produce entanglement. And that's the essence of the argument. It can be done a little more carefully than what I just did, but but basically, yeah, so if you look at this, right, L is finite because we have a finite T block. At small x, this is much bigger than this, right? Because this is 2 to the 0 and this is 2 to the minus L, and L is large. So initially at short distance, this is big, this is small, right? This is the line width, this is the level spacing of the bath. This is the lifetime of the flip rate of the L bit, right? And then the question is, will you eventually get to a distance where this is smaller than this, right? And we've got a 2x here, 2 to the minus 2x here, and 2 to the minus 2x over zeta here. And the only way this is going to stop is if zeta is less than 1, right? If zeta is less than 1, then there will be a distance where these become equal and the avalanche stops. If zeta is bigger than 1, this will just go forever and the whole system will thermalize, right? Actually, what will happen is the avalanche from here and the avalanche from here, neither one will stop. They will meet in the middle and the whole system will thermalize, right? Okay, so avalanche only stops if zeta is less than 1, right? And so this is the criterion on the interactions. They have to be exponential. And not only do they have to be exponential, but they have to be exponential with a sufficiently fast decay rate. Otherwise, MBL is unstable. Okay.
Hey, David.
Sorry, go ahead first.
Oh, sorry, Yujing. Hey, David, so quick question. So you said something about the requirement of the spin interact, the integrable, I don't know what you want to call it, the bits in the MBL.
Yeah.
They also, so they're concerned and they don't flip each other, but I guess they have exponential tails, right? I guess maybe that's not going to matter.
Yeah, they have tails, but the Hamiltonian of the I block, it's really just an Ising Hamiltonian. There's no operators in it other than Z operators. That's what it really means to have these conserved operators. It's just an Ising Hamiltonian with ZZ, products of Z operators, no spin flip operators.
And that's not an exponential statement. That's an exact statement.
Yeah, so there are long-range interactions of the Ising type which decay exponentially with distance.
Right. Okay.
Right. If you can't get rid of the spin flip operators, then it's not MBL. If it's MBL, our understanding of MBL is it's a type of integrability where the localized operators, are conserved. They exist, and the Hamiltonian becomes just an Ising Hamiltonian. The interactions could be reasonably long range. That's okay, as long as they're only Z interacting with Z. And then there's no spin flip operators, and so Z is still conserved.
So to
and
establish
that decay length might be different from this decay length. So this is the decay length for spin flip interactions. So this guy coupling to the tail of this L bit so that it flips it. So it's the off diagonal interaction. The diagonal interaction, which is what you're bringing up, could have a different decay length. I think that's still not clear.
Right. So to show that the system flows under this RG flow, if we show for the regime where it will flow to the insulating phase completely, we would want to then also show that the system is entirely described in terms of these, like the same number of integrable operators, which are Ising-like.
Yeah.
Okay.
Yeah.
Good. Thanks. Yeah.
So excuse me, David. I was going to ask a question. So this is Zicheng. So at the beginning, I think you mentioned that the distribution of the disorder inside the I blocks are not important, so that you can basically model it with a unique localization length throughout the entire system. But
yes.
Suppose if you allow for a distribution in the localization length theta. So could you have a scenario where you actually have a partial avalanche in the system, so that the system is like, it's neither MBL nor completely ETH, but it's like a coexistence of both?
Well, there's been a lot of talk of possible intermediate phases between full MBL and thermalization. And I don't want to rule out that such a thing could exist, but so far there have not been any, proposals that had enough detail to really understand, what's the nature of this proposed intermediate phase. But, what you're bringing up, I'm not going to insist that it can't happen, but nobody yet has come up with a scenario for how that works. So that's.
So can I ask?
And we have a consistent story where the transition is just direct with no intermediate phase. But it's plenty of uncontrolled approximations and assumptions. So I don't want to insist on that. Okay. So
I have a question, if I can ask.
Yeah, go ahead.
So I'm thinking of a similar system, or I want to ask if this is similar. So I could think of a system, a lattice system of fermions without talking about disorder, and I could attach a coupling it like a single site to a thermal bath. And if I sort of go through the Lindblad equation, like create a master equation, I can show that that has to always go to, essentially, I think you can show it goes to a thermal state, or at least if you, it could go to the ground state maybe. So is this a similar?
Well, I'm not coupling it to an infinite bath. So you're thinking of an infinite bath. I'm coupling it to a finite bath, which may or may not be a bath depending upon the energy scale you look at it, right? If you have a finite size system, it has a discrete spectrum with gaps. And if you probe it on energy scales much lower than the gap spacing, all you see is a discrete spectrum, and it doesn't look like a bath, right? And it doesn't act like a Lindblad operator or anything like that. It's a quantum system. It's closed, right? It's only when you probe it on energy scales much larger than the level spacing that it looks like a bath, right? So here we're asking, and that's what all this is about, is it's about, I have a quantum system, is it a bath or not, right? We want to answer that question, right? And here we've got something, it's a finite size region, it's got a certain level spacing, it's finite, so really it's not a bath, right? A true bath is infinite, right? It's got a continuous spectrum, this has got a discrete spectrum, right? So it's only a bath when you probe it on large enough energy scales where that discreteness is unimportant, right? And we're really asking, is this a bath or not? To the nearby L bits, this is a bath. To the far ones, it's not. And there's a point where it switches. If this decay length is less than 1, it will switch, right? And so for the L bit over here, it's coupled to this, but this is not a bath. Whereas the L bit here is coupled to this, and for this L bit, this is a bath, right? And this point where these two become equal is where it switches between those two regimes, right? But we're not, we're not doing Lindblad. We're doing a closed quantum system. This is a quantum system, right? There's no environment. We're actually asking the question of, is this a bath or not? Whereas when you do Lindblad, you're already assuming, yes, there's a bath, right? And of course, if you assume, yes, there's a bath, everything will thermalize. That's true, right? But we don't want to assume that because, that'll just remove the physics we're interested in.
So David,
does that make sense?
Yeah, thank you.
So David, this brings up the question I was thinking about, although I was not very clear. So would this scheme then be equivalent to a system coupled to a finite bath? I can formally define finite bath. There is no problem, right?
Yeah.
Okay.
Well, but it depends on what you mean by a finite bath.
Let's take your spin system. Let's say these are electron spins. I couple it to a finite number of outside nuclear spins, which are not part of my system. The nuclear spins are, doing the diffusion, but they're finite number. They're not infinite.
Yeah. Or let's just couple it to a random matrix of finite Hilbert spins.
Correct. Yeah, exactly. That's what it is, right?
Yeah.
So it's
and then that system may or may not be a bath depending on the situation. Right.
So that makes then a lot of sense. Okay, continue.
Yeah. Because if you're probing it on energy scales where the spectrum of that thing you're coupled to is completely discrete, it doesn't look like a bath. It just looks like a bunch of discrete energy levels.
And the point is, and
the chances that you'll be resonant with some transition in it goes to 0. Yeah. Right. Okay, but let me since we're almost out of time, I don't know how strict you guys are on the time.
Oh, we are not strict on time. It's up to your level, up to your level of energy.
So let me try to keep moving here, because we're getting close to, and I'm going to skip a lot of steps to get to the sort of bigger picture kind of situation here. So there's really two things that can happen. So what we do is we coarse grain the system on the energy scale. And one thing that can happen is I have my T block, I have my I blocks here, and the nearest T blocks to the left and right are very far away, and zeta is less than 1. And so this avalanche just stops. So the avalanche stops. And now what I have here failed, it was acting as a bath, but now we got to the point, oh, it's no longer a bath, it just has a discrete spectrum, right? And so I can just say, oh yeah, this thing just has a discrete spectrum, nobody else is going to get entangled with it. And so I can just say, oh, I'm just going to diagonalize this and make some L bits which are localized in this region. And this just becomes one big I block, right? So we integrate out this T block and just make a bigger I block, which is the combination of this I block, this T block, and this I block, because this guy was unable to really thermalize these two I blocks, just a little bit near itself, but only out to a finite distance, right? So the avalanche stops. And that's one thing that can happen in the RG, and that's actually the most common thing happening near the transition, because these guys are dilute and the nearest guys are far away. Okay, so this is what we call an I move in the RG. As we coarse grain, we realize, no, this isn't a bath. And so it gets localized, right? But now this new longer I block, so this is now a longer I block, right, which is the combination of this guy and this guy with this little bit here. This is insulating, but this end spin here and this end spin here on the T block, this thermalizes well, it's very entangled, and so this guy's strongly coupled to that guy. The interactions aren't falling off exponentially across the T block because it's conducting, right? So this new I block will have a slightly longer decay length than before, because we've put a resistor, a conductor, and a resistor in series, and the effective thing there is slightly less resistive than what you started with, right? And so zeta renormalizes. And this is, if you think about it, it's actually an anti-screening. This T block makes the interactions longer range. So it's an anti-screening, right? We renormalize, the interactions get longer range due to the T blocks which were integrated out, okay? So that's that, and that will generate a flow of this parameter, this decay length. It renormalizes upwards, it moves towards 1, right? And when it gets to 1, the system's going to thermalize, right? Okay, and so we want to know, is it going to get to 1 or is it going to stop before that? Okay, and now the other, so that's one possibility. So this is one possibility as we coarse grain. And it's actually the prevalent possibility near the transition. And then, or, here's our sample. Here's a T block. Here's a T block. They're close together by chance, and the two avalanches meet. Right? You got this end spin here, you got this end spin here, you got this end spin here, this end spin here. You got an I block in between. The whole thing gets thermalized, and so now we get a new T block. So this renormalizes to a T block that's longer. Still have the end spin here, the end spin here. this end spin, all the L bits inside here, they're now kind of hidden, right? Because the rest of the system just interacts with this end spin here and this end spin here, right? So this is the T, I, T to T move. We get a longer T block. And this is our RG. So we let these things happen. You can write it out mathematically as a functional RG. I'm not going to show you all that stuff. Okay. Now I'm going to draw RG flows. So we're going to have, so we really have, remember, a zeta, which is one parameter, and a function for the probability density, the density of T blocks of a given length. Okay, so it's an infinite parameter RG in that it's got a function there, but we're going to define one function, one parameter characterizing this, which is a scaled density of T blocks at the cutoff. Remember, the cutoff is lambda. This is a density per length. So this has dimensions 1 over length squared. And so we define a scaled property of this distribution as the density of T blocks whose lengths are at the cutoff times the cutoff squared. This is dimensionless parameter characterizing part of this, one property of this distribution, and we'll call that Y. Okay. Now, right. So now I'm going to draw some RG flows and talk about, and then compare it to Kosterlitz-Thalès. Okay. So we've got here Y, right, which is a scaled block density, right? And then this other parameter is this zeta, and zeta C is 1, showing you that. And so this is the interaction length. Okay, so this is, first of all, the interactions are exponential interactions. And here they are shorter range, and they become longer range near the transition. Okay. Now, if I don't have any T blocks, I just have a fixed line here, right? Because if I just had all MBL, no T blocks, nothing is happening, as long as the decay length is less than 1, so I get a fixed line. So this is the Mbl phase. The Mbl phase is represented by a fixed line parameterized by the decay length. Now the decay length is a dimensionless number because I've measured lengths in the density of qubits. So the density of qubits is 1. So this is really the ratio of the decay length and the spacing between qubits. Right, so it's a dimensionless number, and so that's why 1 is a special value. If I'm way down here, I just have a very small density of T blocks. They're very far apart. Only this happens. What happens is the T blocks just get integrated out. You never grow big ones. This thing renormalizes a bit, and so the flows just go down onto this fixed line here. And then there's a separatrix, like this, and then the flows go off like that, just like Kosterlitz-Thalès, right? If you have too many T blocks, this happens a lot. T blocks are close to each other, you grow bigger ones, and then the system goes more and more thermal, you renormalize zeta more strongly, and so you either flow down onto the fixed line or you flow off. Looks just qualitatively like Kosterlitz-Thalès, right? But remember, it's, this is just 2 parameters of an infinite number of parameters in a functional RG. okay? And now let me just over here draw Kosterlitz-Salis. So here's KT, okay? And I want to just talk about the differences between these two things. Okay, so here we could call it eta, the power law for the decay of the correlations. There's an eta C, which happens to be a quarter. Here's eta 0, okay? Now this is the vortex density. It's a scaled vortex density, right? Vortices and anti-vortices. And in Kosterlitz-Salis, these two parameters are the whole story. It's not a functional RG and we're just showing two parameters of it. This is the whole story, okay? There's a fixed line. So it's topologically the same structure. One contrast is if we look at the vortex-vortex interactions, they are stronger here and weaker here. Here it's the other way around. As we go from deep in the Mbl phase to the critical point, the interactions between the T-blocks get stronger, whereas here they get shorter range, decaying faster. So that's one contrast. The interactions are power laws, right, as opposed to the exponentials over here. But the flow is qualitatively similar. Right? If you have, now let me just mention a couple of the other contrasts. So here, vortex pairs, which are integrated out, screen the interactions. Right, this is like a Coulomb gas and you have screening, whereas here, like I said, you have anti-screening. And that difference is reflected in here as you go along the fixed line towards the critical point. The interactions get longer range, whereas here they get shorter range. So that's a contrast. Here you only integrate out pairs, and they just integrate to nothing. Right? When you do the Kosterlitz-Salis RG, you find, the way Kosterlitz did it, you find the pair of vortex, anti-vortex pair that's closest to each other, and you just integrate it out, and then you have nothing, right? Whereas here, you have, single T's go to nothing, and that's the anti-screening. And then T pairs are going to a much longer T. So the details of what's going on is rather different. And then of course over here, there really is a functional, here there isn't. Here you write down the beta function in the space of these two parameters, it's an analytic function. Here you write down the beta function in the space of these two parameters, it's a singular function because it's really projecting a beta function which is analytic, presumably only in an infinite dimensional space. Right? Okay, and it makes a contrast. It's a different universality class in a number of respects. The most obvious one is if we look at the correlation length, over here, the correlation length, so say we have a bare coupling G and a critical bare coupling GC, the Kosterlitz-Salis scaling is the correlation length goes as exponential of A G minus GC to the minus a half. So it's got this exponential of a square root singularity in the correlation length. Of course, that is correlation length nu goes to infinity. So it is robust to Harris and Chase et al. If you add disorder, the universality class doesn't change. Whereas over here, when we go through this, the flow is mathematically enough different that the behavior is different. It's actually less strongly in the new correlation length exponent infinity limit, but it still is, and it looks like this. G minus GC to the minus some constant log G minus GC. So it's got this exponent, which is, so it's still nu goes to infinity because it's got an exponent which is going to infinity, but only as a log as opposed to over here where it's square root. So they're both nu goes to infinity, but this less so. And that's what we get from our implementation of this. Okay, so that's sort of putting, what is the physics making this Kosterlitz Thales, and what's the analog in Kosterlitz Thales? Here you have a screening, here it's an anti-screening. And then the specifics of what's going on is different, although topologically the two flows look similar, but mathematically they're different in a number of details. So that's it's an overview. There's not enough time to really dig deeper into it, but I was trying to give you an impression. I don't know, does anybody want to ask anything about that?
Can I ask something?
Go ahead.
Hi. So how can I see that when I increase the randomness, it becomes more localized? Because it seems to me it only depends on like the length of your T blocks, and if it's more uniform, then it looks more thermalized. So how do I see that, how the randomness comes?
Okay, so this decay length, on the bare level, right, say you had particles on the line with random potentials and no interactions, then you could calculate Anderson localization and the localization length of those orbitals. And you need, in order to be in the Mbl phase, so that when you turn on the interaction, it's okay, you need that decay length to be short on the lattice spacing, right? It has to be of order 1 lattice spacing or less, right? And the more randomness you have, the farther you are over here. The interactions decay more rapidly with distance, right? Because we're talking about interactions which are actually local interactions, but they're mediated by this, these wave functions, right? You have a localized wave function which has a tail, and that mediates a longer range interaction, but only with an exponential set by the decay of that tail, right? So basically, by being more localized, stronger randomness makes things more localized, and it makes the interactions shorter range and helps stabilize the localization.
I see. All right, thanks.
So David, this then brings up the question, Shankar, that if I have a given actual physical system defined by Hamiltonian, Hubbard model, Heisenberg model, whatever it is, I don't really know what the critical disorder is where this transition will take place. Is that correct?
That's correct.
Yeah.
That is correct.
All I know, and this is tremendous knowledge, that if I make the disorder large enough, this would happen.
Yes.
But what that large enough is, this theory cannot tell us, correct?
Well, I wouldn't really put it that way. So we do have reasonable numerical evidence that the systems that show Mbl physics in one dimension do flow off to stronger randomness, right? So to see this, we don't need to go to infinite randomness. We need to go to infinite sizes. We need to, right? Those systems you're talking about, with moderate randomness, we believe that if you did a big enough system and coarse-grained it on a very large length scale, this is what you find.
No, I accept this because our theory is quite complex.
That's standard RG
Sure.
lore. Of course, the flows don't have to go here, right? The one way this can be not true for a system is it never flows anywhere near this physics. It goes to some fixed point that's not anywhere near here, right? And that we can't really control. But we do have indication from the numerics that it's headed at least in this direction.
Yeah, that I'm not completely convinced of, having done some of the numerics myself, because what happens, as you know very well, you know better than certainly I do, is that anytime you increase the system size, the so-called critical disorder for a specific model tends to increase somewhat. And so I have never been able to convince myself numerically that MBL definitively exists.
No, I'm not claiming that. I'm just saying if you take the data and look at the probability distributions, you do finite size systems, you do many samples, you measure quantities of interest which are relevant to the localization, and you look at the probability distributions of them and ask, do these distributions, when scaled, get broader as you go to larger systems? Do they become bimodal? So this is something Brian Clark and David Huse noticed. They have some quantities which, in the strong disorder limit, it should be bimodal. One peak for thermal-like, one peak for insulating-like. And they saw the quantities they were looking at were developing this bimodality more and more strongly as they went to larger sizes.
So
you don't need to estimate where the transition is. You just need to ask, as I go to larger sizes,
increasing or not.
Does the probability distributions over samples become broader and broader, in that the samples, the more thermalizing samples and the least thermalizing samples, are they getting farther and farther apart in their behavior? And that seems to be the case. And you don't need an estimate of where the transition is to do that. You just say, in the vicinity of the transition, is this happening?
Yeah.
Right? And that's telling you, oh, there's a flow in randomness that's going towards stronger randomness. And I think the evidence for that is reasonably good. But of course, it's only a flow over some modest range in small systems. So,
but that's why having a theory like this helps. At least we know what's going on.
Yeah, but you have an idea of where you're going, maybe.
Yeah. Second closely related question is that this argument, which is really very, very elegant, very powerful, seems to be applicable only to one dimension. So is this something?
Yeah. So I was going to say a little bit about going away from these assumptions. So that was sort of my last.
Please go ahead. Yes,
thing.
That's that. Yeah.
People obviously will drop out. No, a lot of them haven't. Okay, so now I want to look, so that was about, a system which was specifically one dimension, random, short range interaction, coarse grained to a very large length and time scale, so that we can focus on this sharp transition. And so now I want to back off from all that and just sort of talk a little bit more broadly about what other regimes exist, most of which we really don't understand, but just to sort of set up the bigger picture, okay? So remember, I had this phase diagram, and I'll draw it the same way. More localized this way, more thermalizing this way, okay? And so now what we've got, right, and now the localization doesn't need to be due to randomness. It could be due to something non-random like quasi-periodicity. So instead of calling this randomness, I would call it breaking of translational invariance, right? And quasi-periodicity breaks the translational invariance also and produces Anderson localization as well as many-body localization. Okay, so of course over here, as before, we have an Mbl phase. We have a sharp transition. Okay, and I'll say something about that. And now we have, after the transition, an Mbl-like regime. And that means, what I mean by that is, if you don't go to the joint limits of infinite time and infinite system, but you look in an experiment or in some numerics, this region will still look localized. This transition, you're looking on too short a length scale to see this transition. And then there's some crossover. And then there's the thermal phase, thermal regime. So the idea is both this, and this. This is all the thermal phase. But if you probe it, in experiment, on a finite length scale, on a finite time scale, or in numerics, you find a regime where it thermalizes nicely, on the scale you're looking at and a regime where it doesn't. But the actual transition is back here, okay? So I think that's the general picture. Now, this transition, in most cases, so let me just write it this way, this transition may require taking L to infinity, T to infinity differently from the thermodynamic limit. And we're talking about a phase transition that's not a thermodynamic phase transition. It's only in the dynamics. And to see it, the way you take, you want to take the limit in order to get a sharp phase transition, but you're not constrained that you have to take the limit the way you would do it for thermodynamics. And in fact, what happens in many cases, in order to find this phase transition, you have to take the interactions to 0 as you take either the system to infinity or the time to infinity in order to bring out a sharp phase transition. We're used to this for infinite range models. With infinite range models, the coupling has to be 1 over the size of the system to some power in order to get the proper thermodynamics, right? Already the thermodynamics insists on turning the interactions down as you take a large system. Here, the dynamics ask for it even when the thermodynamics don't, right? And so this is discussed. So there's a nice paper talking about power law interactions, Tikhonov and Merlin, 18, and then Sarangopalakrishnan and I did this more generally. Discussing how do you take the limit in order to get the transition in various cases. We were just doing the random case. And it depends on what dimension you're in, do you have power laws, what exponent do the power law interactions have, things like that. Okay, so that's one comment. The other comment is, if there's a sharp phase transition here, generally people have been assuming that this stuff here is just the critical regime of this phase transition. And that may be the case in some of the cases, but I think we're learning that in a number of the cases, and perhaps even in the one-dimensional case, that's not the right way to think of this stuff. So when one does numerics on the 1D models and studies this transition here, that's what you see. It's not even clear that we should be thinking of that as the critical behavior of this phase transition. Maybe it's some quite different physics. And so I think that's something, we have a good theory of this, ETH, random matrix theory. We have a good theory of this, localized conserved operators. Now we have perhaps a good theory of this transition, at least in some cases. But this stuff here is much less understood theoretically, even though it's what's being studied numerically. And maybe we should separate off the study of this from being part of the study of this. Allow this to be its own physics, which isn't necessarily related to the physics of this sharp phase transition. So I think that's a direction the field might go. I'd like to do something in that direction if possible, but it's not clear what to do. The theory of phase transitions, thinking about the limits, it makes this a lot easier to think about. This is just a crossover, right? And crossovers are kind of ill-defined, and of course it's going to depend on what length scale and time scale you probe it at. So that makes it a lot harder to think about. Now another comment about randomness. The story I told you with these rare T blocks, which were rare regions, which are thermalizing and causing the transition, once your system is non-random, like quasi-periodic, there really aren't any rare regions. So we are expecting and there is strong indications of that the quasi-periodic problem, the phase diagram is actually quite different than the random problem. And again, elaborating on that is I think there's still a lot more to do. There's a nice paper by Gopalakrishnan and Basur and a student doing a sort of RG for the sharp transition for the quasi-periodic problem. But I'm not sure that helps you with addressing this stuff, although that's not clear. I think there's something to do there. Okay, and you could view this regime here as what you might call a pre-thermal, nowadays, a pre-thermal regime, in that it's a regime of behavior which lasts over a long range of time, but ultimately it's going to thermalize. But it's interesting what happens before it thermalizes, right? That's what pre-thermal regimes are. Okay, so that's just some quick comments about what, how this fits into the bigger picture. The avalanche story still applies here, right? So Derook and Huvenier made an argument that avalanches destroy the Mbl phase over a wide range of circumstances, but they were assuming they were taking the thermodynamic limit in the conventional thermodynamic way. Whereas if you give yourself the freedom to not do that, then you can really still have this phase transition. And the phase transition is when the avalanches start. So for a lot of systems, this phase transition is not when the avalanches run away. So in 1D, the transition is when the avalanches run away. We let them start, but they get stopped in the Mbl phase, and then the transition is when they run away. Whereas here, in more than one dimension and with systems with longer range interactions, the transition, which can be sharp, is when the avalanches start, not when they run away. They will run, once they start, they will run away. So you have to stop them before they even start. And that's what determines, that's what we've added to this discussion in this paper with Sarang Gopalakrishnan. And then for the quasi-periodic, since there aren't these rare thermal regions, is the avalanche instability even relevant? Right? Does the system still able to do something like that, or is it totally irrelevant? That's not clear. So there's a lot of open questions here, but I think I'll leave it.
Maybe
any more questions?
Maybe a small comment about this story about two-dimensional avalanches. So there is some numerical work by myself and collaborators, which...
Yeah, so I was going to mention a paper, it's like sorry. I was going to mention a paper by, it's from the Dogen, are you Dogen?
That's me, yes.
What's your first name? I'm sorry.
Elmer.
Yeah, okay. I have your paper written in my notes, but I was truncating. Yeah, so he has done some very nice work exploring this a bit in 2 dimensions and seeing a story, seeing numerical data, which seems consistent with the...
Right.
I think I'm summarizing it correctly. Seems
consistent with this story,
yes. The story that we talk about here, where it has to do with avalanches. That the numerics can be analyzed in a way which makes it look quite consistent with the avalanche story.
Right. So that paper will appear in PRL about this week or so. So yeah, it's a nice opportunity for me to advertise.
Yeah, let me just, so his paper, here it is, 2002 07635.
But maybe it's worthwhile to point out also that also in 1 dimension, there is some indirect evidence suggesting that this avalanche story makes sense. Because on one hand, we can see that if you look at 1-dimensional purely random systems, then from this numeric perspective, it looks like this crossover region is drifting. to stronger disorder
This will drift out towards here as you go to longer.
as you increase the system size, yes. But then when you look at quasi-periodic systems, this does not seem to happen, or at least not as strongly.
It's certainly weaker, yes.
So this seems to be a crucial difference between these quasi-random and truly random systems, which is
Don't call it quasi-random.
consistent also with
Quasi-periodic is not random. It shouldn't be called quasi-random. It is not random, deterministic.
Okay, quasi-periodic, as you wish.
I'm trying to suppress this usage from the discussion. It's a very important difference. And a lot of people call quasi-periodic quasi-random. It's very deceptive in this context because it's very important that it is not random.
That's absolutely dumb. I don't know who does that. But
well, it dates from Anderson localization where, you know, in Anderson localization, the difference is less important, right? It really only becomes a mortal sin when you get to many-body localization.
But there is a subtle difference even in Anderson localization.
Well, in 3D, no, right? So we just
in
3D, the universality class for quasi-periodic and random, they're exactly the same as far as we can tell. There's no rare region effects in standard Anderson localization, at least in 3D.
No, 3D is the same. I was thinking about 1D.
In lower dimension, it matters. Yeah. Oh, absolutely. Yes. Yeah.
So there are many open
Again, that's not rare region effects. That's weak localization effects.
Correct.
Right. Which are there in the random problem, but not really there in the quasi-periodic problem.
So, David, this is Shankar again. I want to go back to the main thrust of your talk, this beautiful paper that you have. I am not understanding something. Why do you need to appeal to Kosterlitz, Thouless at all, except for the fact that that exists?
No, I mean, we're not appealing to it. We're just pointing out that there's a, you know, it has a RG flow which looks a lot like Kosterlitz-Thouless, right? It's
but
you know, when you know, Vasseur and Serbin first noticed this, they sort of just said, oh yeah, the flow looks like this. Let's just assume an analytic beta function. The only thing you can get is Kosterlitz-Thouless. And so they said, oh, it is Kosterlitz-Thouless.
Okay, I know.
So that's there in the literature. And we're saying, no, it's only qualitatively Kosterlitz-Thouless, but mathematically, it's different in a lot of details.
Okay, I now understand.
But yeah, we don't need Kosterlitz-Thouless, but it's enough like Kosterlitz-Thouless that you want to make the comparison and say what's similar and what's different. Also because Kosterlitz-Thouless is just so well known, right?
Yeah, I get it now. Vasseur et al., the paper I did not know, already alluded to that. So elaborating in what sense it's somewhat like that. But to me, if I didn't know about the Kosterlitz-Thouless analogy or that paper, as I didn't, your story looked pretty complete. You have this log-log behavior, which is, as you said, very different from the square root. But I understand why.
Yeah, it's really a historical thing that both Kosterlitz-Thouless is really known to a lot of people.
Mm-hmm.
And then also there was this paper where it was suggested it really is the same as Kosterlitz-Thouless, where they didn't put in enough of the physics for it to be a true functional RG. So you know, they just ended up with that, you know, in a certain approximation.
Okay, if there is any quick question.
Yeah, just one quick question. Is the avalanche story relevant in any way to flow K and Mbl, where we cannot really talk about, you know, energy?
Yeah, this whole story could have been flow K. In fact, I think it's, you know, one should only, you know, if one's only studying Mbl physics and not something else, you should study only flow K problems because you don't want to have extra conservation laws, right? And so let's say my whole talk was only about flow K.
So even though you cannot really talk about energy, but you can still talk about
Well, there's a pseudo energy. It's all very, see, the thing is, all the physics in the RG is very low energy physics, right? And so it's at pseudo energies, which are very small compared to the flow K, the photon energy in the flow K system, right? And so there is an energy, right? It's a pseudo energy. It's only defined modulo 1 photon. But we're talking about energies which are exponentially small, right? And so there's no issue of changing by 1 photon, right? And so at this energy scale, there's no difference between Hamiltonian and flow K, right?
So basically, you still talk about the energy of flipping, and then compare that to the bandwidth of the thermal. I mean, which is a well-defined quantity.
Yeah, just everywhere. Whenever I said energy, just say pseudo energy. Right?
Okay.
Energy modulo 1 photon.
Mm-hmm.
But since we're talking, the photon energy is assumed to be of order 1 in the flow K system, and we're talking about energy scales much smaller than that, so it doesn't make a difference, right?
Okay, thanks.
And the level spacing, right, there's a flow K operator for the T block. It has a level spacing, which is, the phase difference of the eigenvalues. It's a pseudo energy again.
Okay, if there is any more quick question. If not, let's thank David for his wonderful talk. Thanks a lot.
Okay.
So David, your discussion schedule will be Friday and next Monday.
Yeah, I haven't looked at it, but yeah, Friday.
People are still signing up, so yeah.
Good.
Okay, thanks a lot.
See you then.
See
Bye.
you. Bye.